In this video, I want to complete the proof of the differentiability of power series. This was discussed the statement of this theorem was discussed in the Wednesday lecture and concerns a function fx equals an x minus x naught to the n, a power series with positive radius of convergence. And we showed on Wednesday that the series converges pointwise on the full interval. It converges uniformly on parts of the interval for an arbitrary a. And this, as we discussed, this b implies a. And this uniform continuity, even though it holds only for a part, because it holds for every, it holds on the full interval. But what we did not have time to finish was this smoothness part. And again, we will establish smoothness on a part of this interval, except for differentiability, we will need a little bit more room as well. We will need another b that lies between these. So we will establish convergence on A, but we will need a b that lies between them. And this is because when we differentiate the series, we will get these powers of n here. And we will have to show that these can be bounded by something. Okay. So how do we show this smoothness? So the existence of infinitely many derivatives. Well, the most difficult case is actually showing that you have one derivative. Because once you have one derivative and you have the formula with a power series, then you have the same radius of convergence as before, and you can iterate this idea to get the second derivative. So you can go by induction to get this statement. So we want to show that the derivative exists for all n. And this proof will focus on the case n equals 0, and then the induction step n to n plus 1. Okay, so for the base case, n equals 0. So when we don't have base case m equals 0, when we don't have any derivatives, this follows from part B. This is part B. So we want to show that this is true for all 0 r. In part B, we exactly say that the convergence is uniform on that interval, and therefore we get the full interval. Now, the next claim is that we want to go from m to n plus 1. And I want to highlight in this induction. So what is the induction claim here? What do we get to assume? By making the claim stronger, we can assume also more, but on the other hand, we have to also show more. So one thing we want to definitely show is that the derivative exists for all m, but also, and this is the strengthening, that the derivative is given by this power series. So now we want to do the induction step. We want to go, once we know it's m times differentiable, we want to go to m plus 1 times differentiable. And we get to assume in our induction that we have already proven this formula. Indeed, in part of our induction claim is that not only that it's m times differentiable, but that we have this formula true for all on all of these intervals. So once we have this, how do we go to the next derivative? Well, we differentiate one more time, and this will require us to differentiate this series one more time. And when is this justified? For this, what we need is to see this as a limit of a sequence of partial sums. And these are called Gn, capital N. And what we need for those sequence of partial sums is to converge to the limit function. But this we know by the induction assumption. What we also need is that the sequence of partial sums are continuously differentiable, and that the sequences of partial sums, the derivatives of the sequence of partial sums converge uniformly. Now, the partial sums of this expression are polynomials. Therefore, they're automatically continuously differentiable. So what we really only have to show is that the derivative exists, because once we have these three facts, what we can conclude is the derivative of the infinite sum is equal to the sum of the derivative of the individual parts. So we drop another factor of n minus m here, and then decrease the power of x by 1. And this is exactly the formula that we want for this. And this gives us that we're continuously differentiable on minus AA, as long as this power series also converges in the same region. So minus AA for all A between minus R and R. One thing here, I changed the indices to start from M. And the reason for that is, and why that is okay, is that we have this prefactor containing n minus 1, and n minus 1 plus 1. For example, when n is equal to 0, the first factor makes everything 0. When n is equal to 1, the second factor makes everything 0. In general, when n is anything between m and 0. This sum starts producing terms when n is bigger than or equal to m, and those correspond to the terms where the exponent is bigger than or equal to m. When we differentiate, we could start from m plus 1 if we wanted, because this coefficient vanishes at the borderline case. So we are left with out of these three assumptions, 1 is the induction claim, 2 is automatic because we are polynomial, so 3 is what we need to show, so we get that the n plus 1 claim. And let's justify 3. So we want to show that this series converges uniformly on minus AA again, where A is arbitrary. And to do that, we will use Weierstrass M test to find a bound by Mn. And we'll need a little bit of slack. So this is the point which I mentioned earlier, that we need to choose a B between A and R. And it doesn't matter how you choose it, anything will work. But for example, the average between R and A will also work. So let's see, how can we estimate this term? Well, first of all, we split it into three parts that we will estimate individually: n minus m, bn, and x to the n minus m minus 1. Now, each of these can be estimated. First, bn minus 1 is just n. The bn can be expressed in its form, so it's the original coefficient an times all the factors that we got from the differentiation. And then we still have the x to the n minus 1 and n minus m minus 1. Now, this term we estimate as before. Since x is inside the interval minus AA, we can estimate this term by a to the n minus m minus 1. Again, we can, without loss of generality, only consider indices bigger than or equal to m plus 1. Second, a to the an can be estimated by b to the n by the definition of radius of convergence. Remember, this is exactly like we did on Wednesday, that the radius of convergence involved this nth root of an. But this bound works only once we have big enough indices. So this bound can be estimated by that once we have big enough. But again, the convergence of our upper bound does not depend on finitely many terms. So that this bound will start from some index does not matter. See the Wednesday lecture if you want to see that in detail. So it's enough to prove this estimate starting from that index. So what we will do now. Now let's look. We have b to the n times, and actually we should have b to the minus n here. B to the minus n. And we have a to the n. So this is a over b to the n, which is less than 1. So, motivated by that and our previous estimates, such as what we did on Monday, we will estimate this n to the power n plus 1 term here by a geometric thing that is absorbed by the other factor. So we'll estimate n to the n plus 1 by b over a constant times b over a to the power n over 2. And then we're left with a over b to the n and times a minus m minus 1. And here is exactly where we get this bound. I'll skip that for now. You can fill in the details here to get that. But okay, so we get mn, and we want to apply the root test. This is not needed for this now. So let's look at nth root of mn, and only for indices where we are bigger than or equal to capital N. So we are left with nth root of c a minus m minus 1 times a over b to the n over 2. The n over 2 here comes from the fact that you have a over b to the n divided by minus. So you lose n over 2 there. Okay, so we have this bound. So now if we take limit superior, n goes to infinity, nth root of mn. I don't want to take a limit because I don't know that the limit exists, but the limit superiors have exactly the same upper bound. And we have this factor here is converging. This is a constant in n that we have inside there. So the limit of this is equal to 1. And when we take the nth root, here we get square root a over b. And remember, the limit equals the lim sup if both exists. So lim sup on both sides. It's a good exercise to try to prove that that is justified. But okay, what we're left with now is square root a over b. And because a is less than b, we know that square root a over b is less than 1. And by the root test, therefore, sum over mn converges. Therefore, we get that uniform convergence as desired on minus AA. And A is arbitrary, so we get it on the whole space. So the crucial thing here was to come up with a bound where we have a bound coming from the coefficient, bound coming from the polynomial, and then bound of x. And we need to choose the bound for A a little bit carefully so that we can absorb the polynomially growing thing. But otherwise, it's straightforward.